All right, so to continue from last time, we pretty much finished up our implementations for the integer array list, the array-based integer list, and then we remember that we changed that so that it was parameterized, so that it wasn't just holding integers, but now it can hold doubles, it can hold strings, it can hold whatever you want it to hold, and so that you only have to have one implementation for an array-based list here. I wanted to go ahead and quickly remind ourselves what it looked like really quick, just really quick before we move on to an alternative. Remember that we established this block size and we initialized an array of that block size. We had various add elements, add element, add it to the end, add it at a particular index. And all of these things, basically what they did is they checked to see if the capacity of the array was already full. And if it was, it went ahead and created a new copy that was bigger so that it could hold new elements. And then we shifted stuff up. If it was you're adding it at a particular index, right? And if there were 5 things in there and you wanted to add it right here, we made sure that we shifted things down to make room for it. We also kept track of the size. Remember that the size is different than the capacity, right? We also had a getter method, right? The get element at index, remove element at index that automatically shifted things down so that there weren't holes in the list, etc. We also had a contains element and an efficient contains using binary search and a toString method, okay? So what I want to do now is show you one possible shortcoming of this implementation. So for example, what I'm going to do is I'm going to add 1 million elements to the start of the list. Right? So for, what I'm going to do is I'm going to do this randomized. So I've created this list here, foo, and I'll go ahead and create a random number generator here. Random r is equal to new random. Right? And by default, it's seeded with the current time, so it's just going to be producing a bunch of random numbers. And for int I equals 0, I is less than. In fact, let's go ahead and change it from 1 million elements to just 100 elements. Okay. For I running from 100 I plus plus, I will say foo.add element at index 0 and r.nextInt. Okay. So it's just going to go up, generate a bunch of random integers, and it's going to always insert them at the front of the list here. Right. So again, if there are 100 elements here, then we're going to shift those 100 elements down and add a new element here. Shift, add, shift, add, shift, add, and we're going to do it 100 times. Right? No need to print it out or anything. I just want to show you how quick that was. Right? So pretty quick. In fact, we could quantify that by grabbing, just hand wavy here. Let's go ahead and grab the current system time, which is measured in milliseconds. So system start, the start time, system dot current time in milliseconds. And then I will go ahead and time it and see how long it takes to add, say, 100 elements. And then I'll print out that result, system.out.println, the start time minus, or the end time, excuse me, minus the start time, and that's measured in milliseconds. Okay? Remember, if you have any questions, you can go ahead and post to Piazza or to the YouTube live stream. Either one I'll see there. Right? If I go to the right place. There we go. All right, so let's go ahead and run this. And wow, 1 millisecond to add 100 things. Right? Now let's go ahead and change this to n here. And let's go ahead and change it to 1,000 elements. Right? Remember, each element that you're inserting here means that you're shifting all of the other elements down. So that last element that we put in there, we're ending up having to shift 1,000 things down just to add that one more element. So whereas it was taking 1 millisecond before, now it takes 5 milliseconds, right? Still within a blink of an eye. What if we went up to, say, 10,000 elements here? Remember, it was 5 milliseconds for 1,000, and now it's 154. So that's 30 times slower. Right? And of course, you'd want to perform this experiment over and over and over again and take an average. And of course, rule out other things. For example, I'm running OBS right now, which is taking, according to it's only taking 8% of my CPU, but that's a lie. It's way more intensive than that. And I've got an i9 here, but whatever. So 10,000, what if we went up to 100,000? So we increased the size of the number of things that we're putting in tenfold, an order of magnitude more. 10 times as big, would that necessarily lead to 154 milliseconds? 10 times bigger, that's going to be 1,540 milliseconds roughly. In other words, 1.5 seconds. It's more than 1.5 seconds already. Right? What do you think it's going to be? Probably going to be more like 10 to 15 seconds. Right? So yeah, 12 seconds. Right? So in other words, 100 times slower, right? If you pull out your calculators and do the math. Right? I went up by a factor of 10, but it is 100 times slower. Predict if I went up to 1 million. Again, it's going to be 100 times slower. So 12 seconds times 100, that is 1,200 seconds. How long is that? 1,200 seconds is, I don't know either. 1,200 seconds. That's 2 hours, right? So no, not. What am I?
Yeah, I was mixing up earlier, so I think.
I'm not. So 1,200 seconds to minutes. It should be 2 minutes, right? Oh, 20 minutes. There we go. I'll just ask Google. I can't do that math in my head. Right? So 20 minutes. Right? Want to sit here and wait for it? No. All right. So let's go ahead and kill it here. Why is it taking so long? Again, remember at that last one that you add, 1 million, you're shifting over 1 million elements. The second to last one, you are shifting over 999,999 elements, right? So each one of these operations, if you've got n elements in your list, to shift them down is n operations, right? That compounds. If you do this 1 million times, then and you're doing a million shifts each time, roughly, right? Then 1 million times 1 million, we call those trillions, right? That's a 1 trillion operations for this one. What if I went to, what is this? 10 million. 10 million times 10 million is going to be 100 times slower. Again, over. So 12,000 seconds is now going to be 2 minutes or more than 3 hours. Right? 10 million things is not that big. So let's think of an alternative here. The alternative is what's going to be called a linked list. There we go. There we go. All right. So what is a linked list? A linked list is not like an array-based list. Instead, elements are stored in nodes. This is a node, right? And let me create another node here. Actually, no, before I do that. So elements are going to be stored in these nodes. Let's just go ahead and go with integers. Say 10 is stored in this node. Not only that, but we have a reference to the next node here, okay? And for that, I'm going to go ahead and paste another node here, right? And suppose in this one we store, I don't know, 12. Right? And then that one has a reference to another node. Each one of these is a node. In other words, it is a link in a chain, right? Like a chain, you know, a chain, you've got a link here, next link, next link, next link. Each one of them is linked, making a long chain, right? And you can string as many of these together as you want, right? Just to show that it's not necessarily sorted, I'll go ahead and put 8 here, okay? And now this is a linked list. Each node is linked to the next node. That node is linked to another node, etc., etc. We have some terminology here. The first node in your list is the head of the list. The last node in is going to be, well, heads. What's the opposite of heads? Tails. Right? It's going to be the tail of your list. Now, what happens at the end here when there is no next node? Visually, we can just go ahead and put phi here. Right? It goes to nothing. Now, in Java, we're going to go ahead and use null as our indicator that that's the end of the list. Right? So think about how you would build this list. For example, what if I wanted to insert, say, 42 at the head of the list? What are the operations that I would end up doing to support this? What would I have to do to insert 42 at the head of this list? First of all, I have to create a new node, right? And put in 42. Right? So let's write this down as we're going along, right? Create a new node with the element. Right? Now that's all by itself over here. What do we do next? Move. Yeah, let me go ahead and give myself some more room here. All of this stuff. There we go. Move it over to give myself some more room. Now move this up over here, right? In other words, I'm going to make it point the new node here. I'm going to make that refer to the old head, right? So to point the new node to the old head, Okay, done. Now, is that the head of the list anymore? Nope. So what do? I update the head of the list to that guy right there and remove that old reference there. And what have I done? I've inserted effectively 42 at the head of this list. Okay. What if I wanted to insert it at the end? What if I wanted to insert, say, 101 at the tail of this list? Well, what's the first thing I need to do? Now think about this as a list. If this were an array-based list, you would be able to jump to any location that you wanted simply using an index. The first one is at index 0, 1, 2, 3, 4. How do you know how to jump to that guy right there? You know how many bytes each one of these takes. You have the memory address of this one, and so it's going to simply be a memory offset, right? You can jump there. That's called random access. You can jump there immediately for free. Can I jump to the tail of this list for free? Nope. I have to start at the head, then go to the next, right? Traversing this relation here, then go to the next, and then finally, okay, this is where I can insert it. And how would I end up doing that? I would create a new node, put the element in it, right? Find where it needs to be, and then add it as getting rid of this thing right here. Oops. Smaller. There we go. And now I can move it down here. There we go. And it becomes my new tail. Right? What if I wanted to insert something in the middle? Visually, what would that look like? Come on. Paste. Paste. Say that I've already got these two elements here. I don't care what they are, this X and Y. And I want to insert 42 between them. Well, again, what do I need to do? ... You know, you came from somewhere, some direction. You've got to find where you want to put it, first of all. But after you've found where you want to put it, create a new node, and I'll put 42 in here. And now how do I link that in? I need to break two connections now, right? What I need to do is I need to get rid of this association and make it point to the new node. I need to make the new node point to this guy over here, and then take this chain and pull it taut, right? And what will it look like? It'll look, GoodNotes is not that sophisticated. I can't take these two things and pull them apart there and make it look nice, right? But you get the idea, right? It would end up being X, 42, and then Y after that, right? That's enough to get started, okay? Let's come over here and let's actually start implementing this list. I'm going to call it my linked list. My linked list. Right? And what was the point of my my demonstration up here at the top? That if you have an array-based list and you always want to insert at the start, that means that you have to shift things down. With this, did I have to shift things down? No, they weren't stored in an array, right? If you want to create something, all you have to do is create a new node and link it to the beginning. So that offers a potential to do this operation that I was trying to do before of inserting 10 million things at the head of a list. And it potentially has, it could be a lot more efficient, okay? But first we need to design and implement our list. So help me out. What do we need? The head of the list, first of all. Okay, well, what type is the head? What was the picture again? The head is a what? It's this thing that stores an element and a reference to the next thing. That's called a node, right? So, node? Question mark, question mark, question mark? That tells me maybe I should make another class. So let's create a node class first. I'm going to parameterize it because I want it to be able to hold whatever you want. Over here in my pictures, I was always holding an integer, right? I want it to be able to hold an integer or a double or a string or an asset, right? Or a person or whatever you're trying to do. So I'm going to parameterize it so that it's of type T, it holds elements of type T. Private, final, T, element. There's the element that it actually holds. It's of type T, matching this parameterization. It's private, good encapsulation, right? Protecting it from the outside world. I'm making it final because if you create a node and you put something in it, I don't want you ever changing that. Okay? Now, what else does a node have? A node has an element, but what else? What about this thing right here? This reference to another node. Right? So what would that be? A node that holds elements of type T and call it next. Again, make it private. In this case, though, I don't want to make it final because I want to be able to link things together. And so if you're pointing to a next and initially it's null or something like that, I want to be able to change what you're pointing to a new node that I'm going to be able to create. Okay? That suggests a nice constructor, right? Public node. And it'll take an element of type T. This dot element is equal to the given element. This dot next, what should I initialize that to though? Anytime I created a new node over here, what did it look like? What's it pointing to? Nothing. So, what's nothing in Java? Null. There we go. Getters, setters. Let's go ahead and generate those. You'll see here immediately that if I expand all of these, that element only has a getter, no setter. Why? Because I made it final. You can't change it. But get next and set next, both of those make sense. Right? And so let's go ahead and select all and generate all those things. Yay. What's another convenience function that we might want here? So what kind of questions could you ask of Node? Like, all right, give me your element, or what's your next one? What is your next one? How could I rephrase that question? Public Boolean, true or false? Do you have another next one? Has next, right? Here's a really quick way of writing it. How do I know if there's a next or not? If there is no next, it points to null. So if this dot next is equal to null, right? Then it is false. So if it's not equal to null, it is true. If this has a next, then it has a next, right? If it's not equal to null, then it has a next. If it is equal to null, then it does not have a next. Right? Excellent. Okay. Now let's actually use that over here. I parameterized the node so that it would hold an integer, a double, whatever you wanted, right? So I'm going to parameterize my linked list class as well, because that's exactly what I did over here in my my array list class over here. I said, well, what do you hold? You hold integers, you hold doubles, you hold strings, whatever you want to hold. Right? And similar for my linked list here. I'm going to make this into a private node so that you can change it, because of course you'll want to insert things at the head. But otherwise, I'm going to make it private for good encapsulation, right? Protection of data. public my linked list. What should my constructor look like? How do I initialize this head node? If there's nothing in the list, then what should it be? Null. Okay. Now let's add on some functionality here so that we can actually start using this. Public void add element to head, or at the head, or whatever. Right? Am I going to be taking an integer and adding an integer x? Nope. What am I going to be taking? T's. Right? If you want x, otherwise you want element or whatever. I'll go with element because it says add element, not add x. Right? All right. How did I do this again? What was my 3-step process? I forgot to write step 3 here. Right? Oops. You create a new node and you put it in it. You point that new node to the old head, and then you point head to the new node. Right? 1, 2, 3. If you want to, you can outline it. 1, create a new node with the element. Make the new node point to the old head. 3, make the head of the list point to the new node. Okay. Should these comments be left in at the end of the day after I'm done coding? No. This is just an outline of my draft of my code. So create a new node, node t, right? And I'll call it new head, right? Is equal to new node t with the element inside of it. Okay. Make a new node point to the old head. New node dot, oops. Oh, new head, sorry. Dot set next to be this dot head. That's the old head. Right? Make the head of this list, this dot head, equal to the new head. And you're done. Right? Get rid of that, and get rid of that. There we go. To-do documentation, right? Let's go ahead and test it. I'm going to go ahead and get rid of this for now, but I want to come back to it. Let's go ahead and create a linked list. My linked list for integers. Bar is equal to new. My linked list. Elide that away. Bar dot add element to the head. 10, 20, 30, 40, 50. 10, 10. Of course, you can have duplicates if you want. It's a list, not a set. Right? And bar system.out.println bar. Right? So what order would we expect here? Remember that I'm always adding to the head. So what does that end up looking like? I insert 10, but then I insert 20 as a new head. So 20 is the new head. Right? I insert 30 as the new head. I insert 40 as the new head, and 50 as the new head. Right? It should look something like this. When I print it out, is it going to look nice and pretty like that? Nope. Why? The default toString value here. So back to the drawing board here. Actually, if you wanted to check it out and see if it actually worked, what could you do? Debug. I'll debug up to that point, and then over here I can take a look at bar and see what it looks like. Bar has head, and the element there is 50, right? As expected. That has a reference to the next, and that element has a value of 40. That has a next, which has a value of 30. Next, 20, next, 10, and then there's a null value for the next here. So here, right here is my linked list visualized right like this, right? That's not as useful as, say, a toString method, though. If I'm going to do a toString method, I'm going to be printing out a bunch of nodes. So let's do that. Public string toString. And what you can do is you can do some checks here. If this dot element is null, then return null or phi or whatever you want. I'll go ahead and return null here in parentheses. There we go. That looks nice, right? You should do it like this. Else return this dot element dot toString. If element were null, then you would not be able to call the toString method on it, and therefore you would get a null pointer exception. That's why I'm adding this additional check here. Okay. And then it's a design decision. Should somebody be allowed to add nulls to my list? Yes, no. That's a design decision that's left up to you. Okay. Once I've got a toString method on the node class, I'll go ahead and go over to my linked list here. And let's go ahead and go with a public string toString method here. Right. Let me go ahead and change my perspective from more real estate. There. Okay. Suggestions? Well, can I just print it all out? What if I just printed this head, right? Return this dot head dot toString. What would it look like then when I printed it out? 50. Right? What about the next? What about the next? What about the next? Next, right? So what am I going to have to do here? I'm going to have to traverse the list, right? And again, what does that look like? I start at the head, and I concatenate 50, right? That node's value. But then I need to go to the next one, right? Concatenate that value, go to the next one, concatenate that value, go to the next one, concatenate that value, go to the next one, concatenate that value. How do I know when I'm done? I've fallen off the edge of the list, and it's null. In other words, I need some sort of a loop to do this. For loop or while loop? A while? Okay, because we don't know a priori up front how many things are in the list. Maybe that's something that we want to implement. To do, keep track of the size of the list, right? Just like we did with an array-based list, right? All right, good. So while, well, any loop will have three elements: the initialization, the continuation or termination, and work towards that, the iteration, the work towards that termination condition. Okay. So what is my initialization here? I need to keep track of where I am. I need a current node. Initially, that's going to refer to the head. Then I will move it along. I'll then make it refer to the second one, make it refer to the third one, etc. Right? So I need a node of t called current, and I will start it at this list's head. While the current is not equal to null, right? While I've not fallen off the edge of the list, I will, one, concatenate the node's element. Two, move, traverse to the next node. Yeah, we did, didn't we? So let me write it like this first, and then we'll come back and refactor it for that. Right? I'm going to need a string builder here because to concatenate stuff, new string builder. You could just go ahead and go with a string and actual concatenation, but what I'm going to do is I'm going to append stuff. So I'll append the current. So sb.append current.get the element. And then I'll go ahead and append a comma here if you want to, right? Just to separate the elements nicely. Traverse to the next node. Current is equal to current.getNext. Go to the next, go to the next, go to the next. Once you've hit that null value, you break out of this while loop and you return the string builder, whatever you've built up to this point. .toString. There we go. Let's do a quick run to see what that looks like. Ah, nice. We do have that Oxford comma there. If you want to get rid of that, then what would you have to do? You would have to stop one step early, right? And then handle that last one separately. That's where our hasNext will come in, right? So, how could I rewrite this loop now? While it has next, append the current, and then traverse to the next. Okay? Let's see what that looks like. 50, 40. Okay, so there, right? Nice. We are no longer going all the way to the end, but now I need to handle that last one. So SB dot, you break out of this. Let's try it like this here first, right? I believe that this will probably just concatenate 20 at the end. Oh, no, it does. Okay, it went to the next one. Nice. But now, instead of doing that, we can go ahead and get rid of that. Oxford comma. Coding Oxford comma. Right? And neat. What happens with an empty list? Right? If you're going to test this rigorously, you need to make sure that you test all possibilities. What does it look like if you're going to output an empty list? What does it look like if you've added 3 things, or maybe 1 thing to the list? Does it still work? 5 things to the list. Right? So here we should expect an empty list, a list containing 1 element, and a list containing all 5 elements, which we know already works. Exception. Right? So what happened? Where did it happen, first of all? In the toString method, called from, not there, in demo.21. So I'm glad I tested this. Why? Does it work for an empty list? Nope. All right, back to the drawing board. If it's an empty list, what's going to happen here? Current is null. Can you call hasNext on a null object? Nope. So maybe we handle this one a little bit differently. If this dot head is null, right, then return empty. Whatever you want. Right. Now when I run this, ooh, nice, empty, 10, then 50, 40, dot, 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 dot. Now semantically, this doesn't seem, this dot head, okay. I understand what you're doing. If it's an empty list, then you return the string empty. Is there a better semantic way of doing that? This dot is empty? That would make a lot more sense, right? If this list is empty, right? You're kind of reading that in English. Right? Do we have that function? No, I really wish we did, though. Oh, well. Right? Well, as I said in the morning section, I said, if you have a wish list, right? If you make a wish, I really wish we had this method. It's your class, grant your own wish, right? So let me pull out my wand here and grant my wish by making that function is empty. And how do we determine if something is empty or not? Return this dot head is equal to null. If this doesn't have a head, then that means that it's empty, and we return true. Right? Otherwise, we return false. Okay. That looks a lot cleaner semantically, right? Because now we can kind of use almost English. If this list is empty, then return this. Not only that, but you can now we can use this functionality outside the class too. Okay. All right. Add element to the head. Okay. Let me go back to my to-do now. Should we keep track of the size of this list or not? Let's suppose that we have a need to publish the size of the list, get size, right? But we never kept track of it, right? What would this look like? Get size. How would we implement this? Well, I need a size variable. I'll initialize it to 0. Return the size. How do I count up the number of elements in this list? How do I print them out? By the way, here's an answer that I would expect maybe from a really naive way of coding. String s equals this dot toString. And now let's go ahead and split it on all white space. S dot split on all white space. Oh my God, I can't believe I'm doing this. No, I know that they're all spaces. So space, and then what would that be? Length dot length. There we go. What's wrong? Dot length. Okay. And return that. I can't believe I just did that, but I've seen this kind of garbage code before, right? Would that work? Let's find out. Let's play around with this. Get rid of this one. Let's go over to demo here and get rid of that too. I don't want that anymore. I should expect this to be of size 5, right? Dot get size. You see what I'm doing, right? I'm just taking the string representation of this and splitting it up and counting the number of tokens. It works. Is that a sane way of doing it? Probably not, right? So let's rethink that. I iterate through, start at the head, 1, 2, 3, 4, and just go to the next, right? So node t current is equal to this dot head, right? While current is not equal to null, exactly the same loop that I did before. I go with size plus plus, I count that node, and then I update the current to current dot next. Okay? And I return size. There we go. Didn't have to change anything here because of good abstraction. I kept all of those details inside the class, and I still get 5. Is that a good idea, though? Let's find out. All right? So let's go back to our experiment here, where we're adding, say, 10 million things. Let's go ahead and kick it down to only 1 million. Remember, 1 million took 12 seconds. That's perfectly, hopefully it won't take that long this time. And I'm going to change my array list into a linked list instead. Right? And instead of adding an element, add an index. Of course, I need to add element to head, I think it is. There we go. And let's count up the amount of time that it takes to do that. Right? Remember, it was 12 seconds before. Ooh. 0.15 seconds, right? Because it's milliseconds. Better? Yep. Now let's try that 10 million that we thought would take, what was it, 3 hours? Or no, we thought that 1 million would take 20 minutes, right? Something like that. 10 million, and so now it takes less than half a second. This is going to take maybe, 1.5 seconds instead of the 3. I don't have the browser anymore, but it was going to take like 3 hours to do that before, right? Why is it so much better? I'm not shifting anything. I'm just creating a brand new node and adding it to the beginning. But now, let's change the for loop here, right? Let's change it to while foo dot get size is less than, what did I say? Well, let's go with 1 million here. 1, 2, 3, right? So this is nearly exactly the same loop, right? While the size is no longer 1 million, go ahead and add something to the head. Remember, this took like 0.15 seconds, 156 milliseconds. Is it going to be as efficient now? We're back to 20 minutes now. Right? Why? I don't know if I relate the story in computer science when I usually do. The painter's paradox? So you remember the painter that said that, all right, you pay this guy an hourly rate to paint the fence, right? And he starts out really well, right? The first 10 feet are done in a matter of minutes. Great. You leave, you come back, and okay, well, he's only got now, it's been several hours now, and he's only got the first 20 feet done, right? Okay, well, maybe they took a lunch break. You come back, and it's taken now 10 hours to get the next 10 feet done. What the hell is going on here? So he says, show me how you're painting. And so he shows him by dipping the paint into the brush, walking all the way over to the unpainted area, painting, running out of paint, walking all the way back to the beginning, dipping again, and walking back and forth every single time. The solution is pick up the damn bucket and take it with you, right? This is the painter going back and forth every single time. Do I have a million elements or not yet or not? Okay, well, I'll count them all up, right? And nope, I don't have a million elements. Okay, start at the beginning here and then add the element. Do I have enough elements yet? Count them all up again. Count them all up again. Count them all up again, right? And that's why it's taking now, it's going to take literally 3 hours to do this. Right? Stop. Don't do it like that. Let's go back and redesign this. Instead of recomputing the size every single time, maybe we want to keep track of it. This dot size is initially going to be 0. Right? Anytime we add something to it, what should we do? Increment the size. Anytime we remove something, we should, of course, decrement it. We're not there yet. And now I don't have to do any of this. Right? Return this dot size. Now remember, what was going to take 3 hours before? With that one simple thing, done. 0.1 seconds. 0.16 seconds. Right? I can kick this up to 10 million and still be done in 10 seconds or so, instead of, or 1.5 seconds, excuse me, instead of the 2-3 hours that it was going to take. Right? That is 10 million. Yep, 10 million. Right? 10 million is nothing. Right? Okay. So don't. This is going to come in when we start looking at algorithms and algorithm analysis, right? That you'll find that linked lists are good in some regards. They're good as an efficient, whereas an array-based list is not good. It's inefficient, right? And then you flip what your elementary operation is, what you want to time for, what you want to optimize for, and then it turns out that the other list is your best implementation. Right? Okay, great. So yes, I'm done with that to-do. Okay. Now, let's go ahead and add some more functionality. What other functionality do you want here? What about adding it to the tail? What would that look like? Public void add element to tail. T element. Well, first of all, I need to get the tail. Right? Dot, 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 tail node. Dot, dot, dot. Right? Then append the a new node to the end. Right? I'm only keeping track of the head here, so one option would be, and this would probably be the best option in general, would be to keep track of the tail as well. All right? I'm not going to do that though. All right? Let's go ahead and get the tail node manually. Okay? How do I do that? Node t current is equal to this dot head, right? While current dot has next, so it has one more. So am I at the tail yet? If there's something else over here, am I at the tail yet? Nope. Keep going. So current is equal to current dot next. Once you are at a node and there is no current, guess what? You are at the tail. Right? So once you've broken out of this while loop, the current is now the tail. Right? So I need to create a new node. Create a new node. And we've done that before. Node t, a new tail, is equal to new node containing the element. There we go. And now, visually, what did it look like again? Come on, wake up. There we go. If I wanted to add something to the end, what did I do? I've got my tail right, my old tail right here, right? But I'm not keeping track of it, so there's nothing to update. And all I need to do is make that point to the new node. Okay. So current is the tail, so current dot set next to the new tail, and you are done. Get rid of your crufty documentations. Let's try it. Over here, I'm going to go ahead and get rid of this because I don't want to add a million things. Let's go ahead and restore that foo.add element to the tail 10, 20, 30, 40. 10, 20, 30, 40, 50. Now what should this look like? Because I'm always adding it to the tail. 10, then I add 20, 30, 40, 50. So it should be 10, 20, 30, 40, 50. Ah. What did I not account for? In fact, where there, the first one, right? So why didn't we have that problem when we did add element to the head? Because we were always resetting the head, right? It doesn't matter if we set next to be null, right? It remains null. But can we call has next if the current is null because the head is null? Nope. So it's one of those corner cases, right? Those edge cases that we need to take care of. If this list is empty, we need to handle that differently. If it's empty and you want to add it to the tail, guess what? Heads, tails, right? You flip the coin and it landed on the edge. They're the same thing. So this dot add element to head. I don't want to have to write more code, right? I've already got something to take care of that for me. And then, of course, I need to return, right? Because I don't want the rest of this stuff to happen. Let's come back over here. Wonderful, right? Of course, I need to system.out.println. Prove to you that it's actually working. Should be again 10, 20, 30, 40, 50. Excellent. Okay. Add element to the head, add element to the tail. Maybe one more add method. We can do index-based stuff still. It's a list, right? In fact, it should be opaque to us that it's a linked list or an array-based list. Right? It's just a list, right? That's how we use actual lists built into Java, right? So public void add element at index. Index, right? T element and int index. What should we do first? What's a bad index? Less than 0 or greater than the size, right? This dot size. Right, now, again, think about that really quick, right? If there are 5 elements in there, 0, 1, 2, 3, 4, it does make sense to add something at index 5, right? You're just adding it to the tail, right? So if this happens, then throw new, runtime exception, invalid index. Right, there we go. All right. What are some other edge cases here that we could take care of? What does add index 0 mean? Add to the head, else if index is equal to 0. Right? This is just my first idea. We're going to refine this, of course. Add element to the head. Okay, and we're done. Else if index is equal to this dot size, then that means that you're adding it where? Tail. Right. There we go. Otherwise, else, now you need to actually do some work. Dot, dot, dot. Okay. Let's go back to our drawing and again see what that entails, right? Entails, not tails. Right? We have to get an element right before we're wanting to insert it at index I. Say that this is I, right? Now, without that element in there, this ends up being index I. And this is index I plus 1. We want to insert it right here, right? Or right, no, sorry, we're off by 1. Erase that. This is going to be at index I. So when we're done, this should be at I minus 1, and this should be at I plus 1. So in other words, this one was the original I, and now this becomes the I because the index, because we're inserting it right before it. Okay. For a more concrete example, again, let's think about 10, 20, 30, 40, 50, indices 0, 1, 2, 3, and 4. And let's say that we want to insert at index 2. Insert 42 at index 2. What should it look like after? 10, 20, then 42, 30, 40, 50. Right? So what do we need to do is we need to find the index 1 right before it, because we're going to insert 42 between these two. So we actually want to find the index at, or the element at index I minus 1. Okay? Seems like a daunting task, right? Let's write another function to do it for us, to do just a simple thing, right? So public void node t get node at index, right? Because if I actually had that, then that would be actually pretty easy. Node t previous is equal to get node at index, and then I want index minus 1. Right? See what I'm doing here? I'm saying I have a wish list here. I want the ability to get a particular node at a particular index. So again, I'm going to wave my wand and grant my own wish. Right? Get the node at index int index. There we go. Okay. Okay. Help me out. I could do index checking. I'm not. I'll let you give that to you as an exercise. That's the boring stuff. Okay. For int I equals 0, I is less than something I plus plus. Why did you immediately go to a for loop here? Yeah, you know up front how many iterations you're going to go, right? And you're going to want that node. So node t current is equal to this dot head, right? And you're going to want to go forward how many times? Index or index minus 1, I'm not sure. We'll count on our fingers here in a second. But all we're doing is going current is equal to current dot next. We're just traversing to the next node, next node, next node, next node. How many times? And ultimately, we're going to return current. Okay? Now, how many times should we actually traverse? There's where my question was. Right? So if index is 0, should this for loop execute at all? Nope, because we're already at the head. If it's 1, it should execute once, right? So if it's 1, it should be execute 1 time. If it's 2, it should execute 2 times. Right? So what I had before is correct. Right? Okay. But now let's think about this. Public? Yeah. So foo dot, I'm now outside the class, right? It's just a list. I can add stuff. I can get stuff out, but wait a second. I can get a node at index 3, and then I can set next to be null. I'm giving the outside world here the ability to muck with my list. Does that sound like good encapsulation? I've not protected my data here at all. All right, so, I shouldn't be doing this. Go ahead and delete this entire thing. No. Make it private. Private. There we go. I want to use it down here, but I don't want the outside world to be able to use it. Foo.get. Now it's not even an option anymore, right? Excellent. Good encapsulation, protecting your data, right? Otherwise, it would be a leaky abstraction. Node? What the hell is a node? This is a list, right? Oh, it's a linked list? Okay, you've leaked an abstraction out, and now I know something about the inner workings of your list, right? Don't do that. So there's the previous. How do I get the next? Same thing. Node t next is equal to this dot get I. Get the thing at index. Except, do I need to make a function call twice? I needed to get this node right here, right? Yeah, I've already got next, right? Why do I need to call that twice? The painter. Why does the painter need to walk the entire fence twice when he can walk to one and then he can go right to the next slat or whatever they're called, right? Slats on the fence, right? So next will simply just be previous dot get next. Now I've got the previous and the current, and I want to insert right between them. How do I do that? Create a new node, dot, dot, dot. So node t new node is equal to new node element. There we go. I need to make the previous point to the new node, right? And then make the new node point to the next. Right? How do I do that? Previous dot set next to the new node. New node dot next, or sorry, set next to the next. And I just put it in between them. Okay? And then return whenever you're done. Let's see if it works. So the example that I was using was, let's insert 42, add, or dot add element at index. We'll add 42 to index, what did I say? 2? Yeah, 2. And so we should expect 10, 20, 42, 30, 40, 50. Right? Let's print it out. Ah, invalid index. Okay. Add element at index. Let's go back to my linked list. On line 46, we threw the exception. Invalid index 2. There are 5 things in there. 0, 1, 2, 3, 4. It's right there. That's valid. We added 1 when we did it to the head, but did we do it when we did it to the tail? Nope. All right. That should take care of that. 10, 20, 42, 30, 40, 50. Great. Done. Ship it. Good enough. What else should I test for? Test it for adding it at the head. 42. Okay, that works. Test it for adding it at the end, or maybe the penultimate. What is the penultimate? Second to last. Good. So 4, or let's go with 3. There we go. Let's go with 4. There's the penultimate. All right. 42, 50. Let's go with 5 at the tail. Ah, so satisfying. 6. That should throw an exception. We should test for that as well. All right. All right. Great. We've got everything working. Right? No one would fault you if you said, okay, well, go ahead and be done now, right? But lots and lots and lots of code, right? Let's cut some of it down, right? Let's think, I don't know, add element to tail, add element, I don't know. I think it looks good, actually. What I was going to do is going to flip it, and add to head would be insert at index 0, and add to tail would be at insert at index, the last one, and then we would do all the work in this one function here. Do we want to flip it instead? Or it's good enough, it works. Don't touch it. Just as a quick exercise, let's do that. Right? So I will go ahead and get rid. When I commit this, I don't want to lose that code, so I'll go ahead and put it in as commented out here. But add element to tail would be this dot add element at index. Add the element at this dot size. There we go. This one would be for add element to the head would be at index 0. There we go. So you can, oh, you know what? I meant to just comment out the code so that you actually have it. Add it at index 0. Right. Now we have to do all of the work here in add element at index. Okay. This still looks good for checking. But now we don't have these corner cases here. Now we actually need to do all of the work. Okay. Oh, here. There we go. Ideas? We can take care of the corner cases here, but maybe we can fold those corner cases in, right, somehow. I don't know, maybe this will work even with the head and the tail. Let's find out. Remember, we should expect 10, 20, 30, 40. And we don't. Okay. You can't do next. Get element at index. We're adding it to the tail here. So adding it to the tail, we come in here and we try to get element at index, whatever. In other words, previous ends up being null. And when we call, yeah. Previous is going to end up being null here. Okay. If this dot is empty, let's take care of the head. I'm going to go ahead and steal that code up here. Put it right here. There we go. Okay. If it's empty, then we're simply going to create a new head here and be done with it. Maybe that fixes all of our problems. Almost. 10, 50. Ooh. What was I doing there? Add element to the tail. 10. We got all the way down here. Is that correct? 10, 20, 30, 40. No, this is definitely not correct, right? Was it wrong with something with my add element to the tail? This dot size? Nope. Okay. I liked what it was before because it was working. Right? Anyway, if it's empty, then we've taken care of that that case. What else do we need to do? Otherwise, it's not empty, so you need to actually do some work. If you're adding at index 0, that means that you're adding it at the head. And so 0 minus 1, that'll never work. So maybe instead of empty, if this index, if it's empty or index is equal to 0, then we take care of it that way. Okay. Same thing here. So go ahead. Oh. Okay. There. Maybe was that my problem the entire time? Okay. Nope. But it is a little bit better, right? Oh, wait. Do I still have that 6? No. All right. It fails here at 42, but we're also not getting the correct list here. It should be 10, 20, 30, 40, 50, right? All right. So my linked list. If it's empty or if the index is 0, then we insert at the head. Otherwise, we know that it's not empty, or that it, or that we've taken care of it, right? And so we can get the element at index 0, but yeah, if there's only one element in this, then index 0 is not going to. Well, no, if we already took care of it up here, so this should work. Why am I getting invalid index? All right, let's print it out. Plus index 5. Why are you? Oh, same problem as before. This dot size plus plus. There we go. Really? That was it. I think that takes care of all the other cases, right? That was my ultimate goal, to consolidate this down to just. If you can take, there are like 5 corner cases, and if you can cut it down to only 2 corner cases, simpler is better. Right? I think that this works, but I'm not 100% sure. Let's try. Let's find out. Foo.add element to the head, 101, and then print it out again. Okay. Add element to. Well, we already tested all of those. Add element at index, say 3. and 142. So that should be 0, 1, 2, 3. So 30 and everything should be shifted down. So 101, 10, 20, and then 142. Oh, we've got to print it, of course. Yep. I'm 99% convinced that it works. I would only be 99.9% convinced it would work if we had a full JUnit test framework that tested it, and like for 10 elements, every single permutation of combinations, right? And you can automate that pretty easily. But otherwise, it looks good. Right? And is it simpler than having code in 3 different places? Arguably, yeah. This is the one function that actually does all of the work. All of the other functions, all the other methods are in terms of this other function over here, this other method over here. I like that a lot better. Okay. We've got a way to build the list. What else would we want here? A way to what? Okay, to remove stuff. So public void, or maybe t, remove element at index, int index, right? And I'll go ahead and go with a return null with a print to do implement. There we go. What else do we want? So CRUD, create, retrieve, update, and destroy. Create, you can put stuff in, right? We've already got that. You can insert it at the tail, the head, or an arbitrary index. Delete, right? We've got that, or we will after we've implemented it. Retrieve. So t get element at index, int index. Guess what? This dot get the node at the index, and get element. Because I made this one generic function, right? I'm able to reuse that here and return it. And then of course I need to do bounds checking here. ... Actually, let's just do that. Don't even do it as a to do, right? Invalid index, but of course here I would go with greater than or equal to size, because there are 5 elements in there. The valid ones are 0, 1, 2, 3, 4, right? If it is 5 or greater, then that's an invalid one. Right? Otherwise, I'm letting this method do all my work for me, and then I just need to get the element once I've got the node. Remove element at index. Visually, what would that look like? So 10, 20, 30, 40, 50. Let's remove 30 here. Visually, all I need to do is get the node previous to it and make it point to this node over here. Effectively getting rid of that. In fact, with only 2 minutes, it won't even take 1 minute to do this partially. We still need to test it for corner cases here. But all I need to do is the trick that I did down here. Get the node at the previous index, right? Get the next node, or next node, right, is equal to previous dot get next dot get next. There we go. Actually, I'm not even going to do that. Yeah, the next node, right? Well, let's go ahead and do it this way here. Previous dot set next to previous next node, right? There we go. See what I'm doing there? Right? I'm just skipping over it, right? And then return null. Let's actually save it. So node t current, right, is equal to previous dot get next. And now instead of calling it next, let's just call it next, right? And it'll be current dot get next, because I don't want to have, grandfather, grandfather, grandfather. Grandfather is what? Father of a father. I don't want to, you don't say father of the father. You say grandfather, right? So not next, but previous, current, and then next. The current is the one that we want to remove. Okay? So by doing that, we have previous dot set next to the next. But I kept current so that I could go current dot get element and return it when you remove it. Now this is not always going to work. Again, you want to test this, but we can at least, try it. Foo dot remove element at index 1 0 1 2. Let's go with 2. All right. So int x is equal to that. We'll go ahead and print the list after we've removed it, and we'll also print x itself. There we go. So it should print out 20, and then it should print out the list without 20 in it. 20, and then the list without 20 in it. The problem, of course, is, let's go ahead and remove that 101 at index 0. Save that. Okay. Did it work? No. Took out 10 instead. Even though I said 0. Remove an element at index 0. Okay. So there's a corner case that's failed. Right? Foo dot get size -1. Remove the last one. Right? That would be 42. Does that work? Yep, that works. Right? Second to last one. Remember, penultimate. Your word for the day. Right? 50. Right? There we go. Is there a second to last, third to last? Penultimate? Penultimate? I don't know. Language crazy, right? Yeah. Okay, that works, right? So I only really have one corner case that I need to deal with here, and we'll deal with that on Thursday. Right? Remind yourself, to do does not work if you remove the head. ... Right? But it does work if you remove, say, the first element. Remember that was 10, right? And so it does remove 10 if it's the second element. Right, second element. All right, it doesn't work if you remove the head. So we're going to have to work on that next time.